Hello everyone. So I think we should be going live now. We might wait a couple of minutes just as people start to join. And we'll get started at around 5 past. So for those of you who have joined, if you have a look at your browser, you can see you have the option to answer a poll that I've already started. And this will give us some information about who is attending this workshop and perhaps even some information to target future resources to new users. And you can also ask questions throughout the presentation using the live Q&A. If you ask a question in the live QA, you also have the option to thumbs up and thumbs down that question. And the more thumbs up, you can't thumbs down a question, I'm sorry, that's a bit rude, but you can thumbs up it, and the more thumbs up it has, the more likely we will answer that question. And if your question has a lot of thumbs up and we don't answer it straight away, we will probably save it for the Q&A at the end. So we can discuss it more. So fellow presenters, if you see a really good question that will have a good discussion around it, perhaps just star it and we will leave it for the Q&A discussion session at the end. So it's good to see we've got some people answering the polls. Thank you for that already. So I think we might get started. All right, so my name is Kim. I'm a PhD student at the Institute for Marine and Antarctic Studies in Australia. Today I'm going to be taking you through the Biogeochemical Argo float program, which I'm going to shorten to BGC Argo throughout this workshop. This workshop is all about you, so please take advantage of the discussion tools and the Q&A and the polls that I've set up for you and Scar has set up for you using the software that I've provided. Throughout my PhD, I've been focusing on how biogeochemical Argo floats can help me answer my research question, which is how are phytoplankton communities vertically distributed in the Southern Ocean? And more importantly, what are the ecological implications of these deep biomasses in this region? The first chapter of my PhD has recently been accepted in Frontiers in Marine Science and should be published for production in a couple of weeks. So if you want to keep your eye out for it, this paper illustrates how BGC Argo floats help me with my research. And clearly, as you can tell, because I'm giving this workshop, I am a big advocate for the BGC Argo program. And I'm going to tell you just how cool I think it is. More importantly, I hope that I will be able to share some resources with you that I've found have helped me with my so far 2-year adventure with the Biogeochemical Argo float program. And I'd like to thank SCAR and also the Antarctic Gateway Partnership, which is a special research initiative with the Australian Research Council, because they have funded my time in putting together this workshop and exploring and learning about the Biogeochemical Argo float program through a 4-month fellowship and my continuing PhD. I would also like to acknowledge my international colleagues and teachers who have helped me create this workshop and make them the best they could be. And special thanks must go to Macron Cornet, Rafaela Sorzed, and Nancy Williams for helping me with the content. If you're watching this on YouTube and you haven't been able to make it to the live session, feel free to ask any questions and tweet at my Twitter handle, which is BGC Kim, shown in the bottom right-hand screen, with the hashtag ArgoScar20 to ask me any questions, and we'll try and get them answered, and also to discuss or comment if you wish. So we're going to dive in and get started with an introduction to the program. The BGC Argo program was founded on the back of the Argo program, which was established in 2000. This program established a fleet of profiling floats to measure temperature and salinity throughout the water column, and this is the only real way to systematically measure the physical state of the upper ocean for near real-time assimilation into computer models. The aim was to have a global array of 3,000 floats, 1 float for every 3 degrees, which was achieved in 2007, yay. The array is now maintained by deployments of around 800 floats a year by 26 countries, which is a massive international collaborative effort. This data to date has been used to identify areas of increased heat uptake due to climate change, which involves the Southern Ocean. And it is also continuously integrated into weather and ocean forecasts. For example, the Bureau of Meteorology here uses Argo data in all of their forecasts that they distribute to the community. And it significantly improves these forecasts. These are just a couple of examples of how Argo data has successfully improved our understanding of the ocean, with over 3,300 research papers published to date. If you want to learn more about the Argo program, they have a site, and there is a very well put together storyboard at this address at the bottom of the screen. So the core Argo program measures temperature and salinity using a CTD instrument, which is located at the top of the float. The Biogeochemical Argo program measures additional biogeochemical variables. There are 6 core variables that have been identified by the steering committee as important to measure. These are pH, oxygen, chlorophyll fluorescence, nitrate, optical backscatter, and irradiance. I'm going to use these icons, which I've employed the use of IMOS icons as well. So thank you, IMOS, for allowing me to use these icons as to reference these different variables throughout my whole presentation. So take note of what each variable means. This float on the right is a Provor float. It is equipped with 4 biogeochemical sensors to measure 5 biogeochemical variables. The principle of the Biogeochemical Argo program is pretty much the same as the Argo float program. The floats work using an internal bladder and a hydraulic pump that controls the buoyancy of the float, allowing it to move up and down through the water column. The floats typically move in the pattern shown at the right, performing a 2,000 metre ascension profile at the end of a 10-day cycle, and then transmit data via the Argo satellite data network to land to a data acquisition centre. This is a video of a float being deployed in the calm Mediterranean Sea. It's quite cool. A common question asked by the public is, can scientists retrieve floats? In the calm Mediterranean Sea, the French are actively trying to retrieve as many floats as they can to be refurbished and redeployed. It is also a benefit to do this as each float costs around 110,000 US dollars. It can also help improve the data when post-deployment assessments of sensors are performed to see how their performance has deteriorated over time. Now, it's not quite as easy to retrieve a float that has been deployed in the Southern Ocean. This is a clip that I took on a voyage that I was lucky enough to be a part of last year, the Southern Ocean Time Series voyage. And on this voyage, we actually tried to get 2 Biogeochemical Argo floats out of the water, but we couldn't even grab one. The weather, even though it was a bit calmer than the clip that I showed you, it just didn't help, and we didn't have the right equipment to get the float using the RV Investigator. So as a result, that float will probably continue its lifetime and in the end, most likely sink to the bottom of the ocean. So what's the environmental impact of this? This has recently been reviewed by Argo scientists and discussed in a report which is freely available for the public to read. They say there is no method of observing the subsurface global ocean that is more cost effective and less environmentally damaging than Argo. There is no doubt in this. And with the amount of impact these observations have on even everyday lives, the benefits seem to outweigh the costs until we can invent solutions to either retrieve Argo floats or create better platforms altogether with new technologies. The program is truly an international collaboration, and it's possible through the establishment of national representatives who meet annually at global steering and data management meetings. Here they discuss technical details regarding data accuracy, quality control, float performance, and sensor performances, as well as provide directions for the future of the program. The proper thanks should be attributed to the Argo and BGC Argo programs so that acknowledgement can be given to the international personnel and funding bodies that allow the unprecedented wealth of data that we see today. A good example of a statement is provided by Nathan Briggs et al. In their recent paper. A very important aspect of the BGC Argo program is that it's working to ensure that all data follows the FAIR principles, which is that data is findable, accessible, interoperable, and reusable. All data is freely accessible for both academic and non-academic stakeholders, and the community is working hard to standardise and document all processing procedures within the program. Both the BGC Argo and the Argo programs are a part of GOOSE, the Global Ocean Observing System, which aims to provide an integrated and sustained ocean observing system for the entire world. International collaboration, conceptual frameworks, and open access data are all essential to maximising the impact and engagement of ocean observations. This allows a smooth transition to research outcomes that can be incorporated into reports that inform policy, such as the Intergovernmental Panel of Climate Change reports that we all see and hear about. In this way, Biogeochemical Argo supports the bigger picture and contributes to the development of society, not just the advancement of science. The program is still only in a pilot stage, with many years of hard work to go before maturity can be reached. This also requires people like you to venture in and show how valuable the data can be. Research outputs from the wider community over a variety of applications are needed to show funding agencies the value of developing such a program into maturity. And this is one of the reasons why we're holding this workshop today, is to get new users more comfortable with the data, even though it might not be completely perfect and ready for their use, to give you the tools and equip you to be able to use biogeochemical data today. So thank you for listening to that short introduction about the Biogeochemical Argo float program. I hope that it gave a general context around how the program is going in its development and what it aims to do and what it measures. Now I'm going to introduce you to the data, which is much more interesting perhaps to you. So when a float is floating around in the water, this is essentially what the data looks like, coming back to the float, the data acquisition center. So on the left, we have the trajectory of a float that is about to cross over the Kerguelen Plateau in the Southern Ocean. And each time the float goes up and down in a 10-day cycle, it sends back a full vertical profile of the water column to 2,000 meters. I've chopped it off to 1,000 meters because the interesting stuff happens at the surface of the ocean here. And this translates to a trajectory of a profile over time, and you can start to see seasonal patterns forming in this float's life cycle as it transitions over the Kerguelen Plateau. Now, this is just one float. These are all of the floats that have been deployed over time, and just think about the amount of data that these floats have given us. There are tens of thousands of profiles. Some currently sitting in data acquisition centers, and the first variables appear in 2000, even though the BGC Argo program was only officially established in 2016. So this program is not even 5 years old. And it already has an unprecedented amount of data compared to traditional ship-based measurements. It really is quite a useful thing that we are starting to be able to use to the best of its potential. The huge advantage of the increased spatiotemporal sampling from autonomous instruments does come at a bit of a cost, and this cost is accuracy. Sensors are autonomous, and while they're often calibrated pre-deployment, these calibrations often need adjusting to in situ conditions and over time as they experience drift. This is not a huge problem, and a lot of work has been done and is continuing to be done to develop accurate products of biogeochemical quantities for easy distribution to users. So as of 2020, May 2020, there were only 387 floats in the water. The Biogeochemical Argo float program is trying to get to 1,000 floats in the water consistently over time. So you can think of the program still only being at 40% of its target goal. So like I said, users must pay attention to the state of the data and ask themselves how this may affect their research. Users are encouraged to perform their own quality control for research projects and publications, but don't be scared by this. I'm going to take you through the main points that you should begin to consider as you venture into using Biogeochemical Argo float data. We're also trying to produce some cheat sheets that will outline and be our first starting point for new users into the program and the data that it produces. Most of the Southern Ocean data is managed by 3 programs at 3 data acquisition centers. The SOCOM program aims to specifically study the biogeochemistry of the Southern Ocean and its influence on climate using the floats. It represents the most uniform array of floats in the Southern Ocean, and the SOCOM data is available to download as a uniformly quality controlled dataset. Regular snapshots are available via the SOCOM data portal, which I'm going to show you later. And each snapshot is assigned a DOA, ensuring traceability. The French lab at LOV also holds a large amount of Southern Ocean data. They have dedicated a large number of resources towards deploying floats in the Southern Ocean and to understand its biooptics. The focus of this lab has been to use the Mediterranean Sea as a test region for integrating data into biogeochemical models, testing float performance, and among other applications. But their focus also extends globally, and this is why they have floats in the Southern Ocean. Finally, there is a large amount of Australian data in the Southern Ocean. A new sub-facility has just been funded by the Integrated Marine Observing System, or IMOS, in order to quality control available data and forms a commitment to contribute 10% of the global network. The data from this data acquisition network may be less uniform. However, it is quickly developing as the sub-facility settles into its second year of funding. As the program is still developing, quality control procedures may vary between data acquisition centres, and they do in fact. It's important to consider these differences in quality control products by not only reading available biogeochemical Argo resources, but also reading any documentation that is provided by the 3 data acquisition centres or contacting them directly to query data quality. Some basic concepts that I'm going to talk about before I dive into the 6 data variables is the difference between accuracy and precision, which is also often referred to as bias and root mean square error. So the accuracy refers to the deviation of a measurement from its true value, and precision refers to the kind of scatter from a measurement's true value. So this measurement over here, these observations are accurate but not so precise. These are precise and accurate, and these are precise but not so accurate. So this is kind of what the sensors give us in their raw form. Ship-based measurements help to assess and correct the accuracy of sensor data. And to do this, we often correct what we call gain and offset. So gain is just a multiplicative factor that requires 2 measurements in order to correct for, whereas offset is kind of the same, correction is applied across, a constant correction is applied across the profile, no matter what value the sensor has given you. Usually the sensors do have pre-deployment calibration because sensor response does change depending on oceanic conditions, but these are all done pre-deployment, and we as users don't particularly have to worry about this part of the data quality. So the first up is oxygen. This is the most widely measured biogeochemical variable. You can see the global coverage is large. These sensors are fluorescence lifetime-based sensors, except for one of them, which has been put on some floats, but we're not going to talk about that one. It's just important to be aware that that one is on there. And how these work is they have a sensing foil which allows oxygen to permeate and equilibrate with it. And then this sensing foil responds based on the concentration of oxygen within it. This means that there's actually a lag time with these sensors, and the sensing foil is also prone to degradation and decay, which causes the gain to change over time and drift. In situ air calibrations are used against NCEP oxygen measurement climatologies, or if the float doesn't have the capacity to perform an in situ air measurement by sticking its head essentially with the oxygen probe out of the water into the air, then subsurface measurements are corrected based on median world ocean axis atlases oxygen climatology. So in summary, you have to watch the gain on this float, but this delayed mode quality control is quite developed in the Biogeochemical Argo float program. So if there is a delayed mode form of oxygen data within the files, then it should be relatively uniform across all data acquisition centers. Nitrate is the next one, and as you can see, it has very good coverage in the Southern Ocean thanks to nitrate sensors being equipped on all or most SOCOM floats. These sensors are optical-based sensors, so they work by measuring the UV absorption of nitrate in seawater, and which is actually also affected by other species in the water. However, a deconvolution method has been constructed in order to derive nitrate in seawater. You have to, for these sensors, they quite often only have an offset correction that is needed to be done. And this is usually done using ship-based measurements if they're collected on site, or using dynamic climatology, which is what we're starting to call it, I guess. I'm going to explain what these are, but it's essentially estimating what we expect nitrate to be in the deep ocean and then correcting the profile to this expected concentration. This method generally has an accuracy of 0.5 micromole per litre. pH is also mounted on SOCOM floats, and this is why, again, we have a good coverage of pH in the Southern Ocean, but not so much elsewhere. These measurements are made using potentiometric electrodes, which measure the voltage difference across an internal and external electrode, and use an ion selective field effect transistor. And from this, they're able to calculate pH according to the Nernst equation, if anyone's particularly interested. Again, this data is corrected to a deep expected measurement using a dynamic climatology. And usually these measurements have an accuracy of around 0.005 units based on initial assessments of data compared to ship-based measurements. Next up is irradiance, and this includes both photosynthetically activated radiation, or PAR, as well as individual wavelengths. Just any measurement of light comes under this sensor. So you can see we don't have the same uniform coverage in the Southern Ocean as we did in pH, nitrate, and nitrate. And this is because most of this data comes from the French Data Acquisition Centre, who are more interested in biooptics and validating satellite methods of measuring irradiance. So the measurements are made using a radiometer, and they can either be downwelling or upwelling measurements. So with downwelling measurements, detectors are pointed upwards, so they're measuring the amount of radiation coming down to the float. Upwelling measurements have detectors pointing downwards, so they're measuring the amount of radiation coming up from the bottom of the ocean. You might say, well, the sun's up above the ocean, why is there light coming from the bottom? It's because the scattering of water molecules and stuff like that. Like you can still see when you're on top of the ocean looking down into the ocean, because light is being scattered in the water back up into your eyes. These measurements are affected by clouds and waves, and the signals look something like these diagrams here. There have been an initial quality control procedure published in the literature in order to detect these methods. None of these procedures are used in delay mode QC yet, and there are no correction methods currently available for this data. Finally, we have phytoplankton data, which includes chlorophyll fluorescence and optical backscatter. Personally, my favorite kind of data. And as you can see, again, we have good coverage in the Southern Ocean. And these are the next most widely measured variables on BGC Argo floats, because the sensors are actually relatively cheap and easy to mount and reliable, well tested. So let's start with chlorophyll fluorescence first. These are measured using a fluorometer. And how this works is blue light is fired using a laser into the water, which interacts with a phytoplankton community. This phytoplankton community emits chlorophyll fluorescence, which is red. And this chlorophyll fluorescence is a photophysiological response. So the type of phytoplankton, the nutrient state or the stress of the phytoplankton, and the light conditions the phytoplankton are experiencing all affect the amount of red light coming back. So this means that the amount of fluorescence coming back from a phytoplankton community is regionally dependent. Additionally, these sensors are prone to the effects of daytime non-photochemical quenching, which suppresses the fluorescence at the surface of the water as phytoplankton experience some kind of light stress. These sensors are not as straightforward as the previous sensors that I've discussed. The previous sensors are measuring something directly. So they are directly measuring hydrogen ion concentration. They are directly measuring light. These sensors are used as a proxy. So it's measuring light, but it's being translated to a chlorophyll concentration or a biomass. And this has huge implications for accuracy, and this translation is regionally dependent. How much does it vary, you might ask? This paper by Colin Ressler is a good starting point. As you can see, the slope factor, which is a calibration factor of fluorescence to chlorophyll, is 3 times higher in the Southern Ocean than it is compared to the global average, which is represented by this 2. So this is something to consider when doing Southern Ocean research and something to explore further into the future, because the Southern Ocean is actually characterized by strong fronts, and phytoplankton communities vary drastically across these fronts. So you might have a region where this slope factor actually changes quite drastically in a short amount of time. And this has actually been shown in a paper by Christina Schallenberg and colleagues, which was published at the start of the year. Optical backscatter sensors use the same probe as a fluorometer. However, they measure the amount of blue light coming back rather than the amount of fluorescence coming back. Phytoplankton, detritus, bacteria, zooplankton, dust, and even bubbles can all affect the amount of light coming back to the detector. The response is also affected by the size, the shape, and the composition of particles in the water. However, in oceanic conditions, it's still a good regional proxy for particular organic carbon, and it's often used. A really interesting development from science. It's also shown that the spikes in a profile of backscatter can give some information on size. And I'm going to show you a couple of studies in the next bit of the talk that use this data. I think my top tip for understanding your data and reliably using it is to know your sensor. And this is why I've tried to give you a brief overview of how each sensor works for each variable. I was lucky enough to be a part of a training course for biogeochemical sensors last year. And this really showed me the value of doing understanding a sensor and knowing how it works and what affects the response of a sensor coming back. If you have the opportunity to apply for this training course or future versions of it, I would recommend doing so. Also, in the future, I'm gonna give this contacts list a go. So we have asked a bunch of friendly experts to come together to answer questions from new users on biogeochemical Argo variables to try and see what gaps there are in Argo documentation and to help people who feel very stuck or lost by the data. So if you have any questions, feel free to send it to this Gmail, or like I said before, right now you can send them to me on Twitter or in the live Q&A. So we haven't actually got any questions popping up in the live Q&A yet. So feel free to do that if you have any questions from that very fast introduction to the data that I've just given you. Now I'm just going to take a bit of water because that's a lot of talking. And I'm going to try and take you through some of the science now. So rather than focusing on the findings that have come out of papers, I thought it would be interesting to show you a bit more of how the findings came about, I guess, using the data. So the Biogeochemical Argo program aims to try to study or better resolve these 5 research themes: ocean warming, deoxygenation, ocean acidification, carbon sequestration and storage, and marine resource management. Now, this one I think is really interesting and not too much has been done yet in this space, but this relates to understanding where phytoplankton are, so that you understand where higher trophic levels like fish and seals and even penguins might forage, so that you can protect them or you can know where to fish. I think it's a really interesting space. So the program at the moment only has 224-ish recorded publications in their repository. You can see they're steadily increasing over time, which is a good indication that the data is beginning to be taken up by users and we're getting some good science out of it. Just the first thing that I'm going to draw your attention to is a lot of the data is used to evaluate satellite products. And this is related to chlorophyll, backscatter and light, or reflectance mainly. These are the 4 papers, I think, which I'm showing you as good demonstrations of satellite comparisons. And this is where some good value comes from having in situ bioptical measurements, because you can develop an automatic validation system which doesn't require you to go out on ships and validate the optical conditions of the water. I'm just going to talk a little bit about this particular method of using chlorophyll fluorescence to validate chlorophyll satellite products. In the case of chlorophyll fluorescence, this isn't so straightforward, as, like I said, satellites or floats don't infer, they infer chlorophyll from optics, from chlorophyll fluorescence. They don't measure it directly. Satellites also infer chlorophyll from optics, but a different kind of optics. They use ocean color, so the greenness of the ocean, or the amount of green light that is being reflected from the ocean surface. This means that the two don't have a direct comparison, and these regional variations in fluorescence can affect comparisons. This is a figure that we published and presented at the Ocean Sciences meeting early this year. And it's from a transect south of Tasmania in the Southern Ocean, going from Tasmania to the ice edge. And you can see that the yield, or the amount of fluorescence to chlorophyll, is changing drastically as you move from the subantarctic into the polar frontal area, where communities are likely more iron limited, and back into the sea ice zone. So it's an important thing to consider for future comparison if you plan on using biogeochemical Argo floats to validate or extend satellite products. Measurements from biogeochemical Argo floats are also being integrated into biogeochemical models, and the aim from this is to obtain a full 3D view of the ocean and its biogeochemistry. BSOC is the largest effort of this in the Southern Ocean, produced by SOCOM. So far, it has assimilated oxygen measurements from the program, and the goal is to assimilate pH and optical backscatter and chlorophyll fluorescence next, for estimates of carbonic chemistry and phytoplankton. A good value of this tool is that it allows users to study ocean processes without being limited by observation space-time. So it means that even though there was only an observation collected here, you can study what's happening here, because the model extends the information collected from observations throughout the ocean basin. The first product from BSOC is available on the SOCOM website if you wish to use it. The measurements are also being used for interesting climatological models. So this is a paper by Raphael Sozen, one of the people who contributed to this workshop. And she has been able to reconstruct the vertical distribution of optical backscatter using satellite products and the physical state of the water column, as well as a temporal seasonal component. Neural networks are a very powerful tool in order to be able to do this, and Rafaela has put in a lot of work in her career to become proficient at doing this. And what this allows is using the information collected from biogeochemical Argo floats to train this model. Satellite observations can then be extended in three-dimensional space. So you can get at any point of a satellite spatio-temporal satellite coverage, you can get the vertical distribution of backscatter through that, and this can help improve estimates of particular organic carbon or biomass over a global scale. The next topic I'm going to talk about is carbonic chemistry. The floats are very useful for studying this, particularly the SOCOM floats. They only measure one carbonate parameter, which is pH. However, we use these dynamic climatologies that I was talking about before to model total alkalinity as well. Now, I'm going to define what a dynamic climatology is right now. All it is a way to model a variable or a parameter based on other variables in the water column. So for total alkalinity, these algorithms, which are available on GitHub, they are trained using oxygen, temperature, salinity, and sometimes longitude and latitude in order to create a climatology that isn't just based on latitude and longitude, but rather is based on the biogeochemical state. This is really good for capturing the influences of fronts and ocean circulation, because the ocean isn't stagnant. It doesn't just confer to a gridded region. It's a fluid entity, and this is the best way that we are able to date to capture this extra variability and change. Now, once you have these two carbonate variables, you're able to use software which is being well developed. It's called CO2sys, or C-carb in R, and you can then calculate and characterize the rest of the carbonate system. And from this, you can get PCO2, which is interesting because then you can calculate and see PCO2 flux, which, as we know, is really important in constraining and closing the carbon budget, which is what we're trying to do in order to improve our understanding of what happens with climate change and climate variability. This paper showed that using Biogeochemical Argo floats by Seth, who is actually joining us today and will be here to answer questions later on, he showed that by integrating Biogeochemical Argo measurements, the seasonality of the Southern Ocean cycle became clearer, and the outgassing of carbon dioxide around the polar front in winter became quite obvious once you integrated, or more extreme compared to ship-based data only versus when Biogeochemical Argo floats were integrated. Now, the study of phytoplankton has been done quite a bit using Biogeochemical Argo floats, and this is also the area of my thesis. Phytoplankton abundance and distribution can be studied by considering data as a time series in order to understand when and where phytoplankton are blooming, and this is also known as phenology. So the phenology is the study of when and why phytoplankton are blooming and when they decline and why they decline. These plots show the progression of beam attenuation, which is calculated from backscatter. And using this data, we can study the environmental drivers that may drive the onset of blooms and their decline. The vertical distribution of phytoplankton is also of interest. This can help to reveal hidden deep biomasses in the Southern Ocean, which can't be viewed using satellite methods. This paper by Madeline Carranza and her colleagues was the first to reveal the seasonal formation of subsurface buildups of phytoplankton in the Southern Ocean. And they did this by using an automatic classification algorithm in order to sift through the tens of thousands of profiles that have already been collected in the Southern Ocean. So automatic classification algorithms are a very powerful tool when using Biogeochemical Argo float data because of the sheer volume. K-means clustering, neural networks, just simple manual classifications of profiles like done here, where she classified each profile based on their shape, can really help you break down your analysis in an easy to digest way. Using this technique, Madeline Kranzer was able to show that storms or wind actually drove the distribution of chlorophyll and fluorescence and backscatter in the water column. So she found that subsurface maxima or buildup of chlorophyll fluorescence formed only in calm conditions, or more likely in calm conditions when storms didn't prevail. This is a really powerful way of showing how covariate analysis and of using biogeochemical Argo data, so understanding how different variables, environmental variables, correlate with each other to understand how they might influence each other in order to deconvolute drivers, environmental drivers that can control variability. This paper by Adinio used different covariations of different environmental conditions to assign different blooms to a particular origin. For example, if a bloom occurred very close after sea ice retreat, then it was assigned ice influence bloom. This allowed them to identify two interesting blooms in near an ocean ridge, which they concluded was most likely due to a hydrothermal vent outgassing. Possibly one of the most applied science applications of biogeochemical Argo float data has been to study the biological pump. A good overview of this pump and its different components are presented in a paper by Philip Boyd and others in Nature, which was published last year. I'm going to talk you through the different components that have been studied using biogeochemical Argo floats. So fragmentation has recently been studied by this really interesting paper by Nathan Briggs et al. They're able to use the spikiness of the backscatter, like I mentioned before, to deconvolute backscatter and chlorophyll fluorescence signal into large particles and small particles. From this, they're able to measure the amount of decay of the large particle and small particle signal to understand how much of this, or the particle fragmentation rates as particles sink down through the water column. The eddy subduction pump has also been nicely studied by Joan Lort. Gives a good breakdown of the method to do this. He identified subduction events via eddies using the density and fluorescence and oxygen signals. Oxygen signals give an indication of the freshness of this. So by having a larger or a higher oxygen content than the surrounding waters, it's highly suggested that this water was quickly subducted from the surface. Using this classification method, he's able to identify hotspots where these events occur, which is east of the Kerguelen Plateaus, a very large, well-known hotspot. And he's also able to look at the strength of these events, and he was able to quantify an estimate of the amount of carbon that this particular component contributes to the biological pump. Net primary production and net community production has also been studied extensively. Net community production can be studied using nitrate, oxygen, or pH using creative methods. As a time series, the change in oxygen or DIC or pH, to calculate DIC and oxygen over time can give an indication of how much the community is, or the net effect of the community in the upper water column. Really simple way to explain this, sorry, I'll go back, is this orange line is the summer, average summer profile of nitrate, and this winter line is an average winter profile of nitrate, which is outlined in Lionel Artega's 2019 paper. The net drawdown of nitrate, or the net effect between summer and winter, is kind of like taken as the average primary production. So we assume that that is the average primary production of that season. So we convert the amount of nitrate that has been uptaken by phytoplankton in the upper water column to carbon. The microbial component can also interestingly be studied. So there was a study done under here, which really explains the concept. By taking the amount of oxygen decay in the mesopelagic zone, you can get an estimate of the amount of the net community remineralization occurring in this region with the mesopelagic, which can also be used as an estimate of annual net community production over basin scales. The methods around this and the explanations are quite complex, so I would recommend reading this paper if this particular method interests you. Now, finally, in a really interesting and recent development, mesopelagic organisms have begun to be detected using biogeochemical Argo floats. This is because it seems like these organisms are attracted to the blinking lights on the pherometers and the backscatter sensors. So they're attracted to the light and they swim towards it, which doesn't mean that this is a passive measurement. We're not sure what can be done with this data yet, but this paper by Niels Hastings, which was published at the start of the year-ish, shows that these scattering layers, or these signals, very likely come from these organisms. They definitely come from these organisms. So it'll be interesting to see how a biologist, a pure biologist of zooplankton, interprets this data, and if they can be used further in the future to study these organisms. And here is another figure from the paper which shows that these signals, these scattering layers, have a distinct seasonality, which is roughly following what we know about some mesopelagic organisms and their migration cycles. So with that, I think we're going to take a break, and then we're going to come back and I'm going to show you how to actually access the data. So if you haven't already, ask some questions about the data, anything you feel confused by if you've already started to have a look at the data. There are no wrong questions, really. Thank you for listening so far, and yeah, we'll get you stuck into the data after we come back. All right, I think we're back. I'll just share my screen again. So I thought the first thing I would do was take you through to the Biogeochemical Argo website and give that a little bit of a look if you haven't already. So this is what the Biogeochemical Argo website looks like. It is still under development, so you'll notice some things being added or changed. Here is just some general information. Some useful links are going into the measured variables and looking at the general context of them. There are more specific information on each of them, and it is very similar to what I've just told you and in a lot more detail. Down here, we have some initial assessments of accuracy and precision for each of the different variables and the references that they come from. This is very useful if you need to know this before understanding if you can use the data for your particular analysis or if it's going to be able to resolve what you're interested in. Another useful link is under the data. If you click on data management rules, you have a list of DOIs here, and these relate to the processing and the quality control procedures which are used by the program. These are distributed by the Argo data management team, which control how the data is, or recommend how the data should be corrected based on current scientific knowledge. You can see there's still some yellow boxes, so Nitrate and Backscatter currently don't have documentation here because we just don't know enough about it, or we don't know how to best standardize the procedures yet. I should say that I'm not involved in any of this at all, and I'm just a user like yourselves. Next, so there's 3 really good links to have a look at. Next would be this one. So this is an interactive map. And this is a good first point to kind of look at what's happening with the floats. I think I already opened this up on a separate page. Oh, here we go. So here you have a list of floats, and if you know the number of the float that you're interested in, you can type it in here and have a search. Or when the page loads properly, you can hover over and click on a float in a region that you're interested in. And it'll show you the float's trajectory and also the variables that it's measured, as well as its lifetime. Now this float is grey, which means that it's currently inactive, and it probably has been inactive for a while. The green floats are currently transmitting. If you're new to the data, this is a good starting point to have a look and see what's out there. You can see there's a lot. Right. Oh, I believe I went back to the start. Here we go. So from the float to your computer, how does the data actually get there? So when the float surface, like I mentioned, the data is transferred via satellites to a data acquisition center. Now this comes through as the float surface and is run through a decoder, and this yields a C file and a B file. I'm going to show you what these files are in a moment. From this, a real-time quality control is first performed, usually within 24 hours is recommended. And then a real-time quality controlled C file and a real-time quality controlled B file are produced. And these files are then pushed to a global data acquisition center. So there are two GDACs. One is hosted by IFRMA and the other is hosted by the Meteorological Society in the US. Sorry, I don't know what that acronym stands for. And all of these files are pushed to either of these depending on the data acquisition center, and then these synchronize every 24 hours. So all changes made are synchronized between the two. After some time, ideally in less than 2 years, a delayed mode quality control is performed, and this usually involves a visual inspection of the data. From this, a D file and a C file are created, and these actually override the real-time quality control data files. And these are just kind of lost, which is okay because all data from here is transferred to here, and theoretically this should be a better quality data. All raw data is located in in both files. So you're always able to access the raw data of the file, so you can perform your own quality control from scratch if you need to. So first I'm going to take you through data access, and then I'm going to take you through some information about data structure and the R files and the D files that I just mentioned. I'm going to give you some tips and tools about data discovery, which is finding the files that you want, because there are thousands of files in the GDAC. So you want to be able to only download or only access the ones that you really are interested about. I'm not going to talk about ERDAC or threads, mainly because I don't know much about them. And if you're familiar with them, you should be able to access the data through these two procedures without much problem. So like I mentioned, these are the two GDACs. I am going to show you what they look like in the browser. So when you navigate to the FTP address, this is what pops up. So you have a whole range of files here and then some folders. Now we're going to ignore these files to start off with. I'm going to come back to these index files later. But if you navigate through to what we call DAC, so in the DAC folder, each sorry, I'm just going to adjust this so I can actually click on my tabs. Each section is sorted by data acquisition center. So you have, this is the US Data Acquisition Center, AOML, the American Oceanographic and Meteorological, their Data Acquisition Center. BODOC is the UK data center, Coriolis is the French, and CSIRO is the Australian. So for the Southern Ocean, most of the data is within CSIRO, AMOL, and the Coriolis databases. If you navigate to the geo, they're organised in terms of ocean region. And as you can see, there isn't a Southern Ocean region. So Southern Ocean data is actually located in all three of these. So for Southern Ocean research, I've found that it's often of more interest and use to use the DAC directory. If you then go into, say, Coriolis, which is a float that I showed you that went over the Kerguelen Plateau, he was float number 6902735. And this is the data from the float. So there are these this profile folder here and here. This contains only core variables, and this contains biogeochemical variables as well. These have all of the profiles located in one NetCDF folder. So if you're interested in studying floats as trajectories and studying all of the profiles from one float, then this is actually a good way to do this. If you're only interested in particular profiles, or if you'd rather just work with individual profiles, you can navigate to the next subdirectory, which is called profiles. And in here, you find a list of all of the different profiles collected by this float. Now, this float did 343 cycles in 1,077 days, I believe. And it's currently dead. It's been dead for a while, but you can really see that even though this float is dead, it's still got all of this data that's of use to us. These are the D files that I talked about. So there's a D in all of them. So there's a BD, there's a D, and there's a SD. These are the S files, the ones beginning with S. The B files are the ones beginning with B, and the C files are the ones that don't have that extra letter there. These contain only the core variables. So only temperature, salinity, pressure. I think they also contain oxygen. The B files only contain biogeochemical variables. So in here would be any irradiance data, fluorescence, backscatter, pH, and all of that. The S files, they contain all of it. So they contain core data, and they contain biogeochemical data. They've been merged in a way to incorporate this. So if I go back to the presentation, so you're able to access that data by clicking on any of those links, and it will directly download a particular NetCDF file to your computer. Another way is to make a mirror of the GDAC, and this is what we've done using the help from the Australian Antarctic Division. So we actually host all of the Southern Ocean Biogeochemical Argo data that we're interested in on the Australian Research Data Centre. The AAD has a spot in there, and this is where we have the data located. And we're actually able to use software written by the AAD and R to directly access the data without having it downloaded onto our local drive. Now, this is really good because I don't know about everyone else doing a PhD, but my computer is very, very full right now after 2 years of work. And I honestly don't have enough room on my local drive for all of this data. All of the code is ready to view, I believe, on it's all publicly available to view on the Australian Antarctic Division GitHub repository. And if you contact Mike and Ben, they'd be more than happy to, I'm sure, to help understand to implement this in your institution, should you choose to. There's also a synchronization service provided by IFREMA, I think, for Argo data. And I've provided a link. If you go to the Argo website, then there's more information on this here. I want to show you some easy ways to access the data because, yeah, there are quite a few new users out there. And if you've never used a NetCDF file and you just want to see if the data is useful to you before learning all of that, I really like the Euro Argo's tool to visualize data. So this is the tool developed by Euro Argo, and you can choose down here, there's some really nice filters. So you can choose the year of deployment if you have a temporal interest. So if I just want to look at 2019, I don't care if the float is currently active or inactive. I want to look at chlorophyll because that's my favorite. And there's also a really cool way to overlay. You can put sea ice on this, which is of interest to some people, I believe. So you can also choose the year of the sea ice you want in there, and it will overlay that data. This is a cool way if you're interested in studying undersea ice or there's a polynya there. Cool way of seeing where data matches up and if there's any profiles or floats that have drifted under the sea ice during a period in time. Now, once you choose a float that you're interested in, so say I'm really interested in float 5906030. Well, actually, maybe we'll look for our float. So where's his number? There it is. So if we look for our float, we search for him here. We can do that. It was too much. Sorry, I think I killed the internet. I would encourage you to have a play around on this. You can see that there's some really good data visualization tools out there. SOCOM also has their own, so you can play around with this. I've left the links on the presentation. I think that might be best for the rest of this presentation if we steer away from those interactive tools. Okay, so I've told you about the C file, the B file, and the S files. And the purpose of the S file is also to kind of simplify the B file. So the B file is arranged in a way that, oh, I have to share my screen. The B file is arranged in a way that the structure is larger. So each kind of variable that is on the same sampling scheme is stored in its own column, which is labeled as nprof. And the number of levels are kind of like the pressure levels that have been sampled. I'm going to show you in R what this looks like. So I have some code here that I'm happy to distribute, which just very simply downloads a file from the GDAC server. So here I'm looking at profile number 50, and I've already downloaded the data to help make this go a bit quicker. And if I look at the B file, see, it spits out a whole bunch of information at me. And this is telling me what's in the file. So if I start at the header, we have all of these metadata variables, which tells us things about the float number, so the platform number. It can tell us what parameters were measured, the cycle number of the float, and you'll see in here we have a dimensionality for that variable. So if we scroll down to the actual variables that we're interested in, like oxygen, and let's find, we've got pressure here, and then we've got pressure adjusted, which is the quality controlled. So any variable that has adjusted after it has been gone through quality control. Any variable that has QC is a quality flag. So it tells you something about the quality. So here we found oxygen adjusted. So this is delayed mode QC'd oxygen. And you see it's got this dimensionality that I told you about, the number of levels and the number of profiles. And if I look at this data, you'll see that the oxygen data is actually only in one of the columns. So I've already gotten the oxygen data out. I think. No, I didn't. I have to go ahead. So here I'm getting oxygen adjusted using the Netcity of 4 package. And you see it's a big file. So you can't really see a lot in that. Oh, I also got it from the S file. So there we go. Get it from the B file. There we go. So you see the data is only in one column. So this is the sampling scheme for oxygen, and oxygen hasn't been measured in any of the other sampling schemes. So the problem with the B files is that you have to figure out which column the data is in order to get the data, if that makes sense. And yeah, there's the only variable where there is data in all of the files are pressure, because there's pressure information for all of the sampling schemes. So this is a bit of a pain to work with, and I am talking from experience. I started using the data before lovely S files were made. So S files condense the dimensionality, and how they do this is explained in the Argo management documentation. But essentially what they do is they correct for the vertical displacements of sensors, and they move all of the variables onto one pressure axis or one sampling scheme. And how they do this is they linearly interpolate profiles onto this synthetic pressure axis. And this means that for a particular record, which may in the B files look very messy like this, in the synthetic file, there's a lot more co-located biogeochemical variables, which is good because a lot of people want to look at the covariability of different biogeochemical variables to see how different, to study ocean biogeochemistry and to understand what might be driving or the interactions between one variable and another. Now, I think I've already gone over this, the difference between real-time and delayed mode quality control. What this looks like in a real a float that is still alive and still profiling is, if you remember, I showed you my float that I chose, and all of the files in it were delay mode quality control. In reality, when a float is active, only a proportion of the files are delayed mode quality control because it's not happening in real time. There's more data coming out of the float than can be quality controlled by a person physically. So what you get is some files have been a delayed mode and some are only in real time. So this is another consideration that you should use when you're using the data, to make sure that you know what kind of procedure and adjustments have been made to your data. So some final notes on delayed mode quality control. The accuracy of the raw data is not suitable for scientific applications. So you have to think about the things that I told you in the previous talk about data, and the downfalls of the data that might skew your results. And the data management team actually encourages you to perform your own quality control and to communicate with them if you have developed your own procedure that you think might improve the accuracy of biogeochemical Argo float data. The delayed mode quality control is performed to the proper expertise of the data management at the Data Acquisition Centre and the current recommendations enforced by the Argo data management team. You can contact your the data manager of the profiles that you're most interested in if you want to have a look. But you can actually check B files to see what kind of quality control data may have already undergone. So I just quickly constructed this data table which shows the quality control that has been undergone in our float. So QC info, you can see for each parameter, I drew this from the calibration coefficient variable. And this is the scientific calibration. This was the equation variable. This is the coefficient variable. And this is the scientific calibration comment variable. And here data management has in detail shown what has been done for each of the variables in this delayed mode quality control file. So for example, for oxygen, which is row number 4, you can see the comment says that a multi-calibration has been performed before the float was deployed, and the air calibration adjustment wasn't made, but rather the World Ocean Atlas climatology of surface oxygen was used to adjust the gain. So this is a really good way to understand a bit more about what's happened with your data before you use it. Finally, I'm going to talk about data discovery. Now, data discovery uses the index file, which has some really good information in it in order to help you whittle down your data set. So for my data set, I am only interested in floats that have traveled below 30 degrees south. So I use the latitude variable. So this is what the index file looks like. So it's arranged in columns, it's a text file, and I've read it into R, and it has the file name. So you can use this variable to directly download the data from the data acquisition center. So it has the date of the profile, so a time component, and also the type of profile. So if it's a Provol float or a Narvis float, the model of the float, I guess, the institution that manages the data, and the parameters it's there. It also has information on the quality control that has been performed on each of the data. So these index files are not so obvious to the initial user, but this guide is a very good starting point to understanding the file structure and a lot of the stuff that I've talked about today during this. So I think we're going to stop me talking now. And again, I would like to say thank you to SCAR and the Antarctic Gateway Partnership for allowing me to make this talk, and also my collaborators who have helped make this talk, I hope, a useful thing. Some more thank yous are listed here. Again, I'm really grateful to the IOCCP for giving me some training on biogeochemical sensors. And I would also like to mention that I have immensely supportive supervisors who have been really great in letting me do stuff like this. So now we're going to have a bit more of a discussion. If you guys want, we have Joellen here, who is one of the head gurus at SOCOM, I guess. So if you have any SOCOM questions, now would be a really, really good time, because we also have Seth here as well, who worked in SOCOM. Mafon is also here, who is works in the French lab. So if you have any questions about any of the French data, and between us, I think we can answer most questions about, or we have some experience in each biogeochemical variable. And any questions that we can't answer, we will forward on to the people who can. So now's the time. I'm also put out some more questions in the polls if you want to go through and answer them. Particularly what's interesting is I want to know how you think you might access the data. So please ask away.
Can we applaud now? You did
Oh.
great, Kimberly. Woo!
Thanks, guys.
Oh, look, there's Seth's applauding too. I'm sure there's more. You just can't hear them. It's wonderful.
It was
No. Seriously, back in 2012, you doing this workshop is really sort of the fulfillment of a dream that it would just not be some small research project, but become a worldwide network. And that the young people would be carrying it forward and finding new and better and cooler ways to use all the data. So thank you. And excellent work, Kimberly. Really fantastic. I remember coming to the first ever brand new, doesn't even really exist yet, Australian BGC Argo workshop with Phil Boyd and Pete Stretton and Tom Trull and company, and being thrilled that you were planning to do this. And here it is. Ta-da!
Yeah.
Congratulations. Woohoo!
Thank you. Thank you for being so supportive. And yeah, this was so much fun to put together. And
Come on in. The water's fine. Woohoo! Thank you, Kimberly. Really wonderful. I wonder if Seth has more, but I just had to applaud. Yay.
Thank you. Your enthusiasm is greatly appreciated.
No, I learned some stuff too here. This is a really nice overview, and I think a great introduction for what seems to be a group of people who in general, haven't explored this yet. So that's really exciting.
Yeah, it's super exciting.
Really
Thanks, guys, for answering the polls.
Sorry, go ahead, Kimberly. It was just terrific to see the array of applications that you thought so carefully through, all the different ways people are starting to use the data or already using the data or planning to use the data. That was fantastic. And the different kinds of sensors you might find, the different places and deployments, et cetera. This was just fantastic. It made me, honestly, I mean, I use the data all the time. It's completely awesome, but I learned a couple of new tricks. I'm totally good. I was sitting here writing notes to myself, must check out.
That's great. I hope there's many people out there also writing the same notes. Like, please go and look at these papers. They're really, really cool.
Well, it doesn't hurt that you're such an engaging sort of guide leader, come on in and here's how we do it and here's where we go and look at all the cool things we can do and that people are doing. Just wonderful. I'm sure Phil and Pete are thrilled with your progress. It's just fantastic. I'm delighted. I'm thinking we need to do something like this at home.
Yeah, that would be great. But yeah, it's all online, so can I come along too?
Anytime. You are always welcome. The more the merrier. We're making stone soup here, right? Everybody puts in their bed and then pretty soon we've got this vibrant and amazing community doing earth-wrecking awesomeness. It's going to be great. Yeah,
it is. And guys who are listening, yeah, there's quite a few of you. Thanks for coming. Really, really appreciate it. And again, don't be scared to ask any questions at any time. One thing when I first started, I was actually really intimidated and I actually didn't know who to ask anything to. Even with the Biogeochemical Argo workshop, that did help me a lot. But I felt very lost when I first started looking at this data. Very lost. And I think Henry is actually listening at the moment, but Henry is the one who came up with the S files, and I have all of this code trying to figure out how to work with the B files that just now is made so much easier thanks to all of the hard work by Henry and whoever else helped put together the S files. So yeah, I'm sure all of the new users are thanking the data management team for that one.
Yeah, actually, Kim, we have some questions in the Q&A, and it's one very interesting one lately post that say asking how can one be involved in the network and if you still need volunteers and people to work with the data.
Joellen, maybe you can answer that one.
Well, so two things. One, of course, there are new measurements popping their little heads up every day, and new floats being deployed next season. I don't claim to know about all the deployments worldwide, but I am very aware we have 4 more years of funding for SOCOM. We've got they basically have fully funded us through a full 10-year cycle. So another 200 floats, and there are rampant rumors that the National Science Foundation is funding a worldwide effort with another 500 BGC Argo floats, led by our own Ken Johnson and Lynn Talley and company. And this is a $50–60 million effort out of the United States. So we're looking, everybody should be getting in the water here. Absolutely. I personally, I'm working on, benchmarking our system models and our better predictions. We're even looking at the change associated with COVID on aerosols and how that's driving changes in ocean circulation. We're also looking at fully integrating into carbon accounting for the ocean now that we have near real-time information on the carbon fluxes, which may be going worldwide. Again, Kimberly showed this fantastic worldwide data set, but the fact is there still are quite a few holes. And so what we're putting our best foot forward here in the United States. They're hiring BGC Argo research associate at HUI. They're also in the process of hiring at PMEL, at Pacific Marine Environmental Lab at NOAA. They're also, I'm sorry, Kimberly, can I make a pitch? I'm hiring a postdoc.
Go for it.
It's coming out. We've already, money's in the bank. We're ready to hire. They're also hiring at Scripps, Matt Masloff, and the BGC, our Southern Ocean State Estimate Group is also hiring a postdoc, as is the Ocean Group with Jorge Sarmiento at Princeton. So come on in, the water's fine. I mean, we're hiring, there will be more floats. Everybody should be looking at the data because frankly, there just aren't enough eyes on it yet. There is a ton of new data coming out all the time and it's really pioneering. So everybody in. I mean, yes, we have new PIs like Seth, who've got his own group now, and they were postdocs, and now they're Nancy Williams and Allison Gray, and but they're changing the world and how we see the ocean, especially in the biogeochemistry. So I hope everybody's ready to take part in the revolution. Here we go. Amazing to see Australia leading like this too, when there weren't very many countries besides the French and the Americans kind of putting in, they invested. And I am just so incredibly admiring and excited about seeing all of that investment pay off now. It's extraordinary and yay. And wait, watching Kimberly go from, hey, I was lost to, let me lead you in. It's just wonderful.
Thank you so much. I've just, there's a lot of questions that I didn't see. Do you have another one, Lara?
Yeah, there is one that maybe can be related with the future of the Argo network, and it says that there is a recent push to use satellites to look into phytoplankton abundance around the globe. So do you know if there is any plans to pair the Argo biogeochemical flows and the fluorescence data with the satellite data to increase the understanding of the phytoplankton abundance?
Mahon, do you think you can answer this one? Or would you like to?
Yes, I will try to at least assess some point. I know that, thank you, Kim, for your great presentation. It was really nice to have all this summarized and the easy approach. So I would say that some people in the French lab are trying to combine satellite and BGC data, at least to correct and look at the variability between the chlorophyll A on the chlorophyll A related to the fluorescence measured by the float. So at least trying to compare and to see how those two are working together. And now also some study to see, because satellite data are limited at depth, and trying to see if from just the chlorophyll satellite data, we can retrieve what is happening at depths deeper than what is seen by the satellites, using some kind of technique like the neural network from Raphael Sauzet. So that's what I know for now. But yes, I think combining the two is really, really interesting, and few studies are working on it.
Yeah, it's super interesting and something that really interests me as well, because particularly in the Southern Ocean, where not really, there's a large uncertainty actually around how accurate the satellite sensors are and where these inaccuracies are coming from. Compared to other regions, Southern Ocean satellite matchups actually have a very high variability. So we're starting to ask the question, what is driving this variability just in the ocean color algorithms, let alone considering what's happening with fluorescence. So it's very interesting to see like the power of neural networks and other creative methods of calibrating pherometers and the power that they have to solve this really complex problem. So it's super exciting. Is there another question, Lara?
Well, we have a question from YouTube Live that says, compared to the Pacific and the Atlantic sector, how many floats are functional in the Indian sector, Indian Ocean?
Joellen, do you know the answer to that question?
I was just sitting here stumped. I don't know right now. I literally was pulling up the map to double check. There are quite a few. The ones in the Southern Ocean, of course, tend to keep moving. They don't stay where you put them, particularly if they end up in the circumpolar current. Boy, they just head on down the chute. But there are so many out now that there is almost always some. Now, there are other deployments that have gotten up into the subtropical gyre, and those are fewer, and I don't know the number. I can look it up for you, but I don't have it off the top of my head.
You could answer that question yourself using the index files and searching in R. If you're really interested, you can make a latitudinal box and say, ask how many floats or how many profiles are in that particular box compared to outside the box or other boxes. So yeah, get exploring in the data, I would suggest.
The JCOM Ops website is also good for finding numbers of floats and getting lists of floats that you can then download from the DAX. So that's another avenue.
Yeah, I want to apologize again. I don't know what happened when I was trying to show the visualization websites, but the JCOMS one is that one that I haven't explored. So thanks for letting us know that. It's a really good one to have a look at, Seth. Is there another question, Lara?
Yeah, we had some regarding the microbiological genomic diversity. This is possible. There is any chance to include the microbiological genomic diversity along with the floats?
I don't know what you guys think, but maybe this might be a bit too far in the future for BGC Argo to think about.
Yeah, I mean, I know there are autonomous genomic surveys on moorings, and Bari has, blanking on the name of the PI who's done that. But since a lot of those involve wet chemistry and reagents, it's tough to put that on a float that you're not going to recover. But there are other autonomous platforms that would, for now, be better. And I could see sort of one-time use sort of sampling, especially as we get down into microfluidic sampling arrays. But first you have to have the sensor, and then you have to get the sensor working, and then you have to get the sensor on a float that is stable and doesn't need to be collected. So a few steps there. But for those kinds of sensors, that I saw a question about silicon, iron, and there are lots of sensors under development, and there's all sorts of non-standard BGC Argo floats that measure transmissivity or alkalinity or that sort of thing. But so it's not, while this program has sort of a core focus on 6 parameters, there are lots of other people who are in exploring different things. So if you're interested, by all means, you should try and put your favorite sensor on a float, because if it works, that would be awesome.
That is absolutely right. We live in an age of wonders, and microsensors and better batteries are making it so that floats last longer, and you can put more wonderful, weird, and wild new sensors on. The BGC Argo array, and there is a founding documents that you can find on the BGC Argo a page that'll tell you all about with the intention and why we use the basic Argo sampling schedule. And a lot of biologists are very unhappy that it is such a sort of backbone array, but it wasn't really meant to be everything for everyone. It was meant to be the sort of zone defense that allowed us to get the 3D, 4D, if you count time, picture of how the ocean's biogeochemistry is evolving from the bedrock of what we could do now, so as to not miss the major changes that are happening associated with climate change. So this is just meant as that background, that bedrock, the first step. But of course, there's going to be all kinds of wonders coming out. We're just still in the process of getting that global array functioning, just like Argo, so that we know how many floats we need to have deployed to continuously, and where the money and the expertise will come to make sure that these things happen, so that that backbone continues, so that we get the baseline and the change through time as we titrate our ocean and heat it. So I'm looking forward. I know Max Sato has an automated sampler, like to take a whole bunch of samplers to look at genomic diversity in the ocean, and it's sort of a float, but it's not a real-time float. It's not like an Argo float, and ours are nowhere near that kind of, and we don't retrieve them for the most part. So.
For good reason. Yes.
Can you imagine how much gas you'd blow in the Southern Ocean trying to catch a float?
we blew a lot.
It's a little far.
we steamed a day and a half south to meet a float, and also to get away from the storm, and then came back with zero floats, which was sad.
I think it's easier to catch them in the California current, where Ken goes to catch them, and he hopes it doesn't get into the current. It just stays in Monterey Bay. But that's or the Mediterranean, where they'd have to get past Gibraltar. But in the open ocean, particularly with a really active current the way they have in the Southern Ocean, the amount of fuel you'd burn to pick up your float is just not, just doing your carbon budget. That's not a wise use of resources, unless you desperately need the data off that one float.
And if anyone has trouble finding that report, you can flick me an email, and I can send it directly to you. Is there another question, Laura?
Yeah, there are a couple of questions more. When the person asks how many variables can one measure, or which variable?
I'm sorry, can you repeat? How many variables can you measure? So There are 6 core variables. They're not measured on all floats. And like we were discussing before, you can measure as many variables as you want if you put the sensor on your float. But there are differences between particular floats and what they measure. It's up to you how you want to approach the data and what variables you need in order to measure these. But as a rule of thumb, the 6 variables that I talked about today, they're the ones that are most widely available through the network. Do you have anything to add to that, Joellen?
No, just thank you for having us. And what an exciting, I can't tell you, I've already written to Phil and Pete and everybody and told them how much this is awesome. Even though I'll just admit my kids are in bed and I am going to be very soon. It's now 1 in the morning.
Thank you so much for coming so late or early, I guess. And thank you.
Have missed it, Kimberly. Brava. Thank you for having us.
And thank you, Seth, as well. Really, really appreciate it. And Mafon, it's early morning. I think, has the coffee kicked in?
Yeah, it's okay. No, it's fine.
Hello. All right, well, should we finish there? I think that might be a good spot.
Thanks for leading a great discussion and great presentations, Kimberly.
Thank you so much for coming.
Yeah, thank you a lot. It was really, really nice.
Thank you for coming too. Really appreciate it. All right.
Thank you. It was a great workshop. Thank you.
Thanks for helping, Lara.
No worries.